Okay, now that we've talked about a bunch of our theory here for flexure, we're going to move on to how all of this works in design. So that's our yield point. Simplifications for our flexural theory. We are going to ignore any tensile strength of concrete. We are going to assume that concrete is only good in compression. It is not good in tension. And this is according to ACI 22.2.2.2.2. Yeah. Design assumptions for concrete. Tensile strength of concrete shall be neglected. Right. We're going to say 22.2.2.2, which is on page 398. If you go flip to that, it says tensile strength of concrete shall be neglected in flexural and axial strength calculations. Two, that our nominal capacity is reached when our strain in our concrete is equal to the maximum strain allowed in concrete, maximum compressive strain that is, which is 0.003. And that's on the same page. It's the section up, 22.2.2.1, also on page 398. Maximum strain in the extreme concrete compressed fiber shall be assumed equal to 0.003. So this is an important number to remember. And finally, if you go to that next little one, it says the this is actually wrong. The compressive stress distribution. Shall be uniformly distributed over an equivalent compressive zone we'll just leave it at that. And what that means is if we go back here, right, when can I make this like, no, that's not it. If you, over, see, that's what I didn't want to do. If you look right here, this is a, there we go. This is like a kind of a parabolic distribution of the stress. We're looking down here at this compressive stress in the concrete. And whereas before, if it was like that nice little triangle, you know, 1/2 base times height, that's easy to find the resultant compressive force. This little distribution, it's parabolic, not so nice. So instead of assuming it's this parabolic distribution like that, we are going to take this area and make it into an equivalent rectangular uniformly distributed area. Right. All right, if we take this to find the area to get that compressive force, we're going to make it into an equivalent uniformly distributed compressive zone. Right. This is a parabolic compressive stress distribution, and this is our equivalent uniform compressive stress distribution. The areas should be equal to the same. It's just a lot easier to find that area, right? It's easier to find an area of a rectangle than an area of a partial parabola. And this is all in ACI 318 22.2.2.4. Continuing down that page of assumptions, page 398. it's going to tell us how we're going to create that uniform distribution. So our assumptions are concrete has no tensile strength. We're going to set our concrete strain to 0.003, and we're going to distribute the stress as a uniform rectangle as opposed to the parabola that it actually is. And that uniform distribution is called the Whitney stress block. These things need to be like the same height. I don't know why they're not the same height. If this is the actual neutral axis, right? The height of our Whitney stress block is going to be less than the distance from that's our extreme compression fibers. Down here we still have our steel as our tensile force. Alright, there's my neutral axis here. This is how the Whitney stress block is used to create a nice uniform stress distribution. Rectangle. Rectangle. The value of the stress, right? This is K3 F prime C. I don't know. All from some experimental data from over a period of time. Now we're going to assume that this distance, so the magnitude of your stress, right, is 0.85 F prime C. So 85% of my compressive strength. That is the uniform compressive stress. The height over which that occurs is called A. The height from the extreme compression fiber to the neutral axis is called C. Remember back from our my over I or MC over I. From the extreme compression fiber to the neutral axis. Cross section where we have zero strain. A is the height of our stress block. Of our Whitney stress block, equivalent stress block equivalent so that, right, this area is equal to that area. Area 1, right, area 2. That's all we're doing here is we're trying to find a way to find area 1 so it's not that terrible parabola. And like formula for the height of our stress block is beta 1 times C. It's some value times C. We'll talk about what that beta 1 value is in a minute, but it's some factor times C. So the two things to remember are 0.85 F prime C is the magnitude of this stress, the height of the magnitude of the stress block, the height over which that stress occurs is beta 1 times C, where C is the distance from the extreme compression fibers to the neutral axis. It's called the Whitney stress block. Not the whiskey stress block, the Whitney stress block. So let's look at our forces. If we just said this was 0.85 F prime C magnitude, and this height was A, then my compressive force C, I didn't write the A. My compressive force is the magnitude, right? This is 0.85 F prime C, the magnitude of that stress times the height over which it occurs, times, that gives me, right, if this is in PSI and this is in inches, I need 1 more inch to get it into just pounds. So my other value that I need is the width, right? I'm basically the magnitude of it, that's A. The width of the beam is B. That's my area that I'm multiplying the stress by 0.85 F prime C. So this is my stress, 0.85 F prime C. F prime C is a stress, it's your compressive stress, it's in PSI. And it's being multiplied by the area over which it occurs, which is A times B. So inches, so that would give me pounds, right? Pounds equals PSI times inch times inch. And if my A is equal to 0.8, or I'm sorry, if my area is equal, if my A is equal to beta 1 times C, I have 0.85 C times beta 1 C times V. On the bottom, I have some force in my, some stress in my steel, Fs, and I know that I have some area of steel, As, so my tensile force is my stress in my steel, Fs times As. Fs is the stress on the steel, As is the area of the steel reinforcement in the cross section. Alright, if you think of the 0.85 F prime C is your stress in your concrete, Fs is your stress in your steel, A times B is your area of concrete over which that stress occurs, As is your area of steel over which the tensile stress occurs. And the other thing that we need to know is where do these occur, these forces. This distance would be A over 2, because if the height is A, so the distance from the extreme compression fiber to the centroid of the compressive stress, or compressive force, the centroid of the compressive stress, which is the compressive force, of the concrete is A over 2, and then the distance from the extreme compression fibers down to the centroid of the reinforcement is D. Right. C is our distance from extreme compression fibers to the neutral axis. A is the height of the stress block. Our equivalent stress block, which equals beta 1 times C. And D is the distance from the extreme fibers to the centroid of your tensile steel, or tensile reinforcement, tensile steel, whatever you want to call it, which is also known as AS. And A over 2 is our distance from the extreme compression fibers to, I guess, the centroid of the stress block. That's just mechanics and materials stuff right there, right? Just writing stuff down again in case you need to a reminder. So those are our forces. This is our compression force. And this is our tensile force. We've got a compression force from the compression stress in the concrete in the top half of the cross section, and our tensile force is all coming from the steel. Remember, we're ignoring any tensile strength in concrete. Recall earlier, we're going to set those equal to each other, C equals T for equilibrium, and that is how we will find our capacities. So this beta 1 factor is, we can look at ACI table 22.2.4, I'll just write it down. Table 22.2.4.3, which is on page 399. This is a good place for a tab. Absolutely. And our beta 1 factor is based off of our compressive strength of our steel, or of our concrete, sorry, F prime C. F prime C and our beta 1. For an F prime C of between 2,500 PSI and 4,000 PSI, our beta 1 factor is 0.85, and that is generally the land where we live. 4,000 PSI, 3,000, 3,500. As you increase your F prime C, you decrease it. Well, that can't be right. Let's look at it this way. F prime C, if you're greater than 8,000, you have a beta 1 of 0.65, and if you're in between, you interpolate. So if you have really high strength concrete, the height of your stress block is going to decrease, because, right, 0.85 versus 0.65 times the distance to the neutral axis. If you're in the middle, you interpolate, which is 0.85 minus 0.05. This is all in that table. F prime C minus 4,000 divided by 1,000. Obviously, F prime C is in PSI. So, anytime you see F prime C, it's in PSI. Good rule of thumb to remember. So, lower strength concrete, larger stress block, higher strength concrete, smaller stress block, as indicated by our beta 1 factor. finally, we're going to look at our minimum required area of steel. ACI says if you want to design with us, you got to play by our rules. You got to put a minimum amount of steel in there. This is another good tab to have. We are on page 135, 9.6.1.2. Page 135. Please keep this tab. And also note that you need to turn the page. I actually have written on my you can write in your ACI 318. It is yours to keep, so write what you want. I have written in there, turn the page, because there's an A and there's a B, and the B is on the next page. Our minimum required area of steel, AS min, is the maximum of, it should be the larger of A and B, is what it says. AS min shall be the larger of A and B, unless there's something else going on. If AS provided every section is at least 1/3 greater than you need. Okay. The maximum of 3 square root F prime C over Fy times BW times D or 200 over Fy times BW times D. F prime C in PSI, Fy in PSI. Basically, if 3 square root F prime C is greater than 200, you use the first one. If it's less than 200, you use the second one. And this is all assuming your yield stress is less than 80,000 PSI. We have to limit it to 80,000 PSI. BW is the width of your section. There's commentary in there about what to use for your BW. For a statically determined beam with a flange, the value of BW shall be the smaller of the flange, or 2 times the width. It's the width of your beam. There's commentary on for a flanged section. Your width of your beam is the minimum of the width of your flange or 2 times the actual width of your beam, which would be if you have a flange section, like a T. T is what you're generally going to have. Right. That is the width of your flange. We'll get to flange sections at the end of in a few weeks, but and we'll come back to this. That's if your flange is in tension. So in this case of the section that I drew, that would be negative moment. And again, this is AS min. This is your minimum tensile reinforcement. Right? Let's see. Not AS prime, AS. So that's introducing us to the code. I'm going to stop here, and next we will start talking about actually analyzing a section. So what did we talk about? We talked about simplifications, how we're ignoring the tensile strength of concrete. We're going to assume the strain in our concrete is the strain of cracking, which is 0.003, the compressive strain in our concrete. Right, EC is our compressive strain in concrete. ECU, ultimate compressive strain. Meaning at which it begins failing in compression. How we're going to take this parabolic distribution and make it a rectangle, which is called our Whitney stress block, which has a magnitude of 0.85 F prime C and a height of beta 1 times C. Beta 1 depends on your F prime C, your compressive strength of your concrete. The forces, compressive force is 0.85 F prime C AB, or 0.85 F prime C beta 1 C times B. F prime C, that little c is a subscript. Beta 1 times C. C is an actual value. It's our beta 1. And our minimum area of steel is based off of our material properties, F prime C and Fy, and our dimensions, the width of our beam, and the depth from the extreme compression fibers to the centroid of the tensile reinforcement.